Hello everyone, welcome to my channel GVS Chem. In this module, let us discuss the bomb calorimeter and numericals based on this bomb calorimeter. Please subscribe to my channel, like, share and comment on my videos. Measurement of energy changes or heat changes. There are two types of heat changes, that is energy change at a constant volume or heat change at constant volume QV. Similarly, energy change at constant pressure QP. These energy changes, the measurement of these energy changes using an experimental technique is known as calorimetry. So, the energy changes associated with the physical or chemical changes can be measured by using an experimental technique, and this process is known as calorimetry. This process is carried out in a vessel known as calorimeter. How these measurements are made? These energy changes can be measured by measuring the temperature. Temperature changes. Now let us learn about calorimeters. This is a bomb calorimeter. In this bomb calorimeter, this is a thick steel chamber, also referred as a bomb. And this calorimeter is immersed in a water bath. This complete setup is known as a bomb calorimeter. To measure the temperature, here a thermometer is immersed in water, and this is the stirrer to make the uniform temperature all along the water. And here two electrodes R1 and R2 are immersed in the reaction mixture. So this is a vessel or a small plate to place the reaction mixture, and this reaction mixture is made in contact with these electrodes. These electrodes are supplied with energy. Heat is supplied here, therefore the substance which is under investigation burns and combines with oxygen. So this calorimeter is filled with excess of oxygen. The excess of oxygen is at 20 to 25 atmospheric pressures. So pressure 20 to 25 atmospheric pressures. Sample. So the pressure is maintained at 20 to 25 degrees, 20 to 25 atmospheric pressure. The sample under investigation is kept in a plate. So this is the plate to keep the sample. Two electrodes are kept in contact with the sample. So these are the two electrodes. When the current passes through these electrodes, the sample under investigation combines with oxygen and produces heat. This heat is absorbed by this water. Therefore, the temperature of the water is raised, and the rise in temperature is measured by thermometer. The thermometer used here is very sensitive. Even if it raises the temperature by 0.1 degree centigrade, that is enough. The rise in temperature by 0.1 degree centigrade is enough to make the calculations. Heat evolved during the combustion of the substance raises the temperature of water, and this temperature is measured by thermometer. If the heat capacity of the material used for making the calorimeter is known, and also if the heat capacity of water is known, then delta U can be measured. In this bomb calorimeter, the bomb, that is the steel chamber, is kept in the substance is kept in a sealed container, and the bomb calorimeter is completely sealed. Therefore, there will be no change of volume. So volume changes are 0. That is delta V equal to 0. So under the condition of delta V equal to 0, the temperature is raised. That is, heat exchange takes place. Therefore, heat exchange at constant volume is called change in internal energy, that is delta U. Therefore, delta U equal to C into delta T into M by W. See here, C is the specific heat, delta T is the change in rise in temperature, M is the molar mass, and W is the weight of the substance. So once again I am writing here delta U equal to C into delta T into M by W. The notation for this. So here delta U equal to C into delta T into M by V, where delta U is the change in internal energy, C is the heat capacity, M is the molar mass of the substance, and W is the weight of the substance kept in the bomb calorimeter. Based on this experiment, let us do a problem. 250 grams of a sample of octane, molecular formula of octane is C8H18, is burnt in excess of oxygen in a bomb calorimeter. The temperature of the calorimeter rises from 298 Kelvin to 304.73 Kelvin. If a heat capacity of the calorimeter is 8.93 kilojoule per Kelvin, calculate the heat transfer. Also find the delta U and delta H of the reaction at 298 K. The equation given here is C8H18 plus 25 by 2, that is 12.5 molecules of oxygen gives 8 molecules of carbon dioxide and 9 molecules of water. Now let us do the solution. Here rise in temperature of calorimeter equal to 304.73 minus 298. How much is this? 6 point. The temperature rise in is 6.73 Kelvin. Now the heat capacity of a calorimeter is how much? 8.93 kilojoule per mole. Therefore, heat absorbed by calorimeter equal to Q equal to C into delta T. See how much? 8.93 into delta T, 6.73. This is equal to 60.1 kilojoule. Substance under investigation is octane C8H18. Molar mass of octane C8H18 is atomic mass of carbon is 12 into 8 plus atomic mass of hydrogen 1 into 18. Therefore, this is nothing but 114 gram mole. Heat produced by 1.250 gram of octane. Whatever the heat produced by octane, all that heat is absorbed by calorimeter. So that is 60.1 kilojoule. Therefore, heat produced by 1 mole of octane is equal to 60.1 into 1.250 by molar mass of substance is 114. That is molar mass of octane equal to Q into weight by molar mass. So if we calculate this, we get 5481.1 kilojoule. Therefore, this if it is simplified, we get the value 5481. So this is nothing but heat exchange takes place at a constant volume, because in bomb calorimeter volume does not increase. Heat exchange at constant volume is nothing but QV. This is nothing but delta U because delta V equal to 0. Therefore, work done is equal to P delta V equal to 0. So delta H equal to delta U plus delta NG RT. What is NG? NG is nothing but delta NG is nothing but number of gaseous moles of products minus number of gaseous moles of gaseous moles of reactants. So if you observe the equation carefully, how many number of moles of gaseous reactants and products? Gaseous reactants are only carbon dioxide. So let us write the equation once again. C8H18, this is liquid, plus 25 by 2 oxygen gives 8CO2 plus 9H2. So here gaseous moles, this is gas, whereas this is liquid and this is liquid. So HR, number of moles of gaseous reactants 25 by 2, that is 12.5. Whereas HP, gaseous moles of products equal to 8. Therefore, delta Ng equal to 8 minus 12.5 equal to minus 4.5. Minus 4.5. Now, if we apply these values here, delta U, how much we got? 5841. Delta U, we got 5481.1. Therefore, delta H equal to delta U plus delta Ng RT. So here, delta U how much? Delta U 5481.1, and here delta G is minus 4.5. So this is minus 4.5 into R 8.314 into temperature 298. Therefore, if we calculate after simplification 5402.24 kilojoule. So this is an example problem under the bomb calorimeter calculations. Change in enthalpy. Change in enthalpy means delta H. Delta H can also be determined by using calorimeter. So here this is a formed polystyrene cup which closes the calorimeter. The reaction mixture is taken here in this calorimeter vessel, and the thermometer is used to measure the temperature raised. The reaction is carried out in a calorimeter which is here the calorimeter is kept in open to atmosphere, Atmosphere means delta P equal to 0, therefore volume increases. The temperature of water bath. This is the water bath. The temperature of the water bath is noted initially. And final temperature is also noted. Therefore, if we know the initial and the final temperatures, we can find the rise in temperature or change in temperature. Right? Knowing the heat capacity of water and calorimeter system, if we know the heat capacity, so here heat capacity of calorimeter and water. If we know the heat capacity of calorimeter and water, so using the formula we can find delta H. Before doing the numericals, let us list out the formula. Heat capacity is denoted by C. Q equal to C into delta T implies C equal to Q by delta T. So heat capacity means amount of heat required to raise the temperature by 1 degree centigrade. Now specific heat capacity. Specific heat capacity means this is represented by small c. Specific heat capacity is nothing but the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree centigrade. Therefore, specific heat capacity equal to heat capacity by mass. Heat capacity by mass. What is heat capacity? Heat capacity here it is Q by delta T into 1 by M. So this is nothing but Q by M into delta T. Now another one is molar heat capacity. Molar heat capacity. Molar heat capacity means amount of heat required to raise the temperature of 1 mole of the substance through 1 degree centigrade. So molar heat capacity is nothing but heat capacity by number of moles. Heat capacity by number of moles. Heat capacity is nothing but C. C by number of moles here. But what is C? C is nothing but Q by delta T into 1 by N. Therefore, this is equal to Q by N into delta T. Therefore, this is an important formula. And of course, this is also important formula. So, this is another formula, heat capacity. Now, finally, relation between internal energies. Delta H equal to delta U plus delta N or T. What is delta N? Delta N is nothing but number of moles of gaseous products. Number of moles of gaseous products minus number of moles of gaseous reactants. So, if delta N equal to 0, delta U equal to delta H. If delta N is negative, then delta H is less than delta U. So, these points also you have to keep in mind. Let us do another problem. 0.08 gram of sample of glucose, that is C6H12O6, is burnt in a bomb calorimeter assembly. A rise in temperature was observed from 25.11 degrees centigrade to 27.21 degrees centigrade. If delta H for the combustion of 1 mole of glucose is minus 2803 kilojoule per mole, calculate the heat capacity of the calorimeter assembly. So here the given data is, sample given here is 0.08 substance. Therefore, mass of the substance equal to 0.08 gram. What is the substance? Glucose. Therefore, molar mass of glucose. Molar mass of glucose. Glucose formula C6H12O6 equal to 180 gram per mole. 180 gram per mole. Now rise in temperature. Rise in temperature, that is change in temperature, equal to 27.11 minus 25.21. This equal to 2.1 Kelvin. Now, what is the molar mass meaning? Molar mass means 1 mole of the substance gives this much amount of heat. 1 mole of glucose means 180 grams. So 180 grams of glucose gives the energy minus 2803. Minus 2803. But what is the sample given? 0.08. So this is 0.08 gram. How much? So here this is 0.08 by 180 into 2803. This equal to, if we calculate this, we get 1245.77 joules and of course this is in kilojoules. We converted this into joules. Now first of all, let us write the equation for the reaction. So equation C6H12O6, this is solid, plus how much this is 6O2, that is oxygen is in the gaseous state, therefore we get carbon dioxide 6 moles, this is gas, plus water 6 moles of water, this is in liquid state. Therefore gaseous moles of products is 6, gaseous moles of reactants is 6. We know the relation between delta U and delta H. Therefore, delta H equal to delta U plus delta nRT. What is delta N? Delta N equal to gas moles of products minus gas moles of reactants. Gas moles of products minus gas moles of reactants. So delta N equal to NP minus NR. NP means number of gas moles of products and number of gas moles of reactants, equal to, this is number of gas moles of reactants is 6. Since here water is liquid, only carbon dioxide is in gaseous state, therefore 6. And in reactants only oxygen is in gaseous state and glucose is in solid state, therefore this is equal to 0. Therefore delta H equal to delta U plus delta nRT. Delta H, how much we got? Delta H equal to delta U plus, this is 0 into RT, this is nothing but delta H equal to delta U. Therefore this is change in internal energy. Change in internal energy. Change in internal energy is nothing but QV. Right. But QV, how do we calculate? Q equal to heat capacity into rise in temperature. So what is the amount of heat absorbed here? Just recollect, this is 1245.7 is equal to heat capacity CV into delta T. So 1245.7 equal to CV into delta, rise in temperature is nothing but 2.1. Therefore CV equal to 1245.7 by 2.1. This is nothing but 593 joule per Kelvin. Therefore heat capacity of calorimeter equal to 593 joule K minus 1. Let us do one more problem. 20 gram of NH4NO2, that is ammonium nitrate, is dissolved in 250 gram of water in a coffee cup calorimeter. When a temperature was recorded from 303.1 Kelvin to 298 Kelvin, find the value of heat absorbed. The specific heat capacity of water is 4.2 joule per K minus 1. Assume no heat is absorbed by the calorimeter. Now, what are the given information here? So, the falling temperature is falling temperature equal to 303.1 minus 298 equal to 5.1 Kelvin. This is nothing but delta T. Mass of water. What is the mass of water given? 250 grams. Specific heat capacity. What is specific heat capacity? The amount of heat absorbed by 1 gram of any substance to raise the temperature by 1 degree centigrade. So specific heat capacity of water equal to, how much it is given? 4.2 joule K minus 1. So heat absorbed amount of heat absorbed equal to heat absorbed Q equal to C into M into delta T. What is C? Specific heat capacity. Here this is C, this is M, and this is delta T. So what is C here? 4.2 joule K minus 1, mass 250 gram, delta T 5.1 Kelvin. Kelvin K minus 1 get cancelled. So what is this? If you multiply this, finally we get 5.5355 joules. 5355 joules equal to 5.355 kilojoule. Subscribe to my channel, like, share and comment on my videos. In the next module, let us discuss the different enthalpies involved in the chemical reactions. Thank you.